Okay, so good morning, everyone. So we shall resume the lectures. So last time I introduced the definition of topological recursion, which I will call here. And I showed you some examples of computation, especially regarding the Airy curve, which is here. I showed you that first you can somehow just press the button to get some, this is an example. If you want to find omega 0.5, well, this gives you a big rational fraction. And the coefficients are the so-called intersection numbers. Okay, so now let me go to the next part, which is, so I will first introduce a few more definitions and talk about general properties and show you how to compute these things graphically, a little bit like Feynman graphs, and then start again with applications. And in particular, an application I will be interested in is going towards the notion of quantum curves or WKB expansions, because it's an important application of topological recursion. And also maybe I will have time to somehow prove the Bertrand's recursion. So I was in chapter 2 of my lectures about topological recursion, and now it will be about section 4. Right. And I will talk about some properties. So, first property. So, let me write what. It's a proposition. I will not give the proof now, at least not now, and I will just take some results. So, the first thing is that, well, when we started with random matrices or with counting triangulations and so on, omega g, in fact,
J'ai un problème.
Okay. When the definition of omega gn came from random matrices or triangulation like that, we knew it.
Non. Coupé. Dans celui-là, attends, j'ai même un essai. Là.
Okay.
Oui, now you can work. It was Larsen.
C'est juste pour l'image.
Larsen loop. Sorry.
Okay, so sorry about that. So I was going. So I was saying that in many applications we knew in advance that the omega gns were symmetric or had to be symmetric, and they satisfy this recursion. And we proved that they satisfy this recursion. Here now we reverse the point of view. We start from an arbitrary spectral curve. And we don't know if there is an enumerating problem associated with it. And there is no reason a priori why omega gns will be symmetric. In particular, given the definition, Z0 plays a very different role compared to all the other Zi's. So it is not obvious at all that the result will be symmetric in all the variables, including Z0. But this is a fact. This is a fact. Omega gn is symmetric. Is symmetric in its n variables. Well, the proof is by recursion, of course. I will not do it. So that's the first fact. The second fact is that for 2t minus 2 plus n positive, quickly positive, omega gn has poles only at zi being one of the ramification points. So, for example, in the Airy case, you see that the omega gns are rational fractions with poles only at the zi is equals 0. And 0 was the ramification point. For quadrangulations, there were the ramification points were at +1 and -1s, +1 and -1, and the omega gns have poles at +1 and -1. Okay. So that's the fact. And moreover, the residue in every variable when zi goes to a, the ramification point of omega gn is 0. So they are poles without residues. Well, here in this example, this is obvious because there is no 1 over z. It's 1 over z square, and in fact, it's easy to see that it's even. Right. Another important property is homogeneity. Imagine that I change my spectral curve and I change y to lambda y. And I don't change x, I don't change b, I don't change anything. So this is what I will call, this spectral curve S. Okay. This is what I will call S to lambda S, which just means multiplying y by lambda and nothing else. Okay. Then if I do that, on this one, the proof is kind of trivial. The only place where y appears in the recursion formula is in the denominator of k. So each time you act with this operation, you do this operation, if you have multiplied omega 01 by lambda, you get an extra 1 over lambda. And so you get as many 1 over lambda as the number of times you have to repeat the recursion formula to get your omega gn, and this is exactly equal to 2g minus 2 plus n. So then, which means that omega gn of lambda times your spectral curve is lambda to 2 minus 2g minus n omega gn of your initial spectral curve. So basically, if you change y to lambda y, y to lambda y, if you multiply y by lambda, and lambda is any non-zero complex number, then the omega gns are multiplied by lambda to the 2 minus 2g minus n. This is another property which is nice is the Dilaton equation. And the Dilaton equation is the following. If you take the sum at all branch points of residue at A of omega gn, and this will be for n pretty larger than 1, omega gn of z1, okay, let me say n pretty larger than 0, omega gn plus 1, z1, zn, and z, times, I will say in a minute that is f01 of z, is 2 minus 2g minus n, omega gn of z1, zn. And where f01 is any function that is defined locally near A, such that its differential df01 equals to omega 01. It's what it is. So if you take the Dilaton equation, So if you somehow contract omega gn plus 1 with a primitive of y dx, then you get 2 minus 2g minus n omega gn, always. And this is for n strictly positive. And the reason why I take n strictly positive here is just because, in fact, the recursion formula which I wrote here was a definition of omega gn only for n. So here I needed n larger or equal to 0. So in fact, this defines every omega gn with n strictly positive. But the idea is that, okay, could we define omega g0? Well, if we use the Dilaton equation, in the Dilaton equation, we take the Dilaton equation to be the definition of omega g0. So this is what I'm going to do.
When you have F01, so you think that omega 01 is not necessarily close to.
Yes, it's not close in general. But okay, I wanted to say I'm going to talk about that right now. So indeed, does this definition make sense? So indeed, when I write that df01 is a function but whose derivative is y dx, whose differential is y dx locally, as just you remarked, omega 01 is not necessarily a closed form. And even if it were a closed form, f01 would be defined only up to a constant, an additive constant. But remember that omega gn plus 1 has residue 0, has no residue. So if you add a constant to f01, you will this constant will be multiplied by 0. So the constant doesn't matter. And also omega 01, indeed, if it's not a closed form, in fact, what you need here to do this computation is only a value of is only the function of f01 in the neighborhood of the ramification point. So you could have, indeed, if it's not closed, there could be monodromies, which means that you can define it in a neighborhood. Then when you come back, it comes, when you come back to the same neighborhood after going around the surface, maybe there is a monodromy, maybe you have added a constant, but again, this does not matter because the residue is 0. So in fact, this is well defined all the time, and it does not matter which primitive you choose locally. So, okay. So, yes, there is another property I wanted to mention. Another property is the special case of, so let's say a formula for omega 03. So in fact, for omega 03, remember that omega 03 in my definition was, by definition, it was sum over A, residue when Z goes to A, K A of Z0 Z times, and here we had we have B of Z, here let me put Z1, and here let Z2, B of sigma A of Z, Z3, plus B of Z, Z3, B of sigma A of Z, Z2. That's the definition of topological recursion which I erased. But in fact, notice that B has no pole at the ramification points, and K has a simple pole. So in the end, it's easy to compute this residue because residue of a simple pole is just like evaluation at the simple pole. And if you do so I let you do the computation carefully, but what you will find is that the sum over A belongs to R of -1 over let me write it this way: x second of a y prime of a times. Let me call it product of a equals one. I equals 1 to 3 of BA of ZI on BA of ZI. BA of Z will be just somehow the B evaluated at A, where one of the two variables is evaluated at A, but when you do that, you will get a differential form. So you need somehow to divide by something to make it a function of Z. And when there is a way to do that, it's residue when Z prime goes to A of 1 over square root of x of Z prime minus x of A B of Z prime. So it's a differential form of Z prime. You can compute the residue, and somehow it's just going to evaluate this as Z prime equals A. So in so for example with the array curve, so where x was Z square, y was Z, and B of Z1, Z2 was Z1, Z2 over Z1 minus Z2 to the square. The ramification points was A equals 0, which I recall sigma of Z was minus Z. So if you do this computation, what do you find? You find that GA of Z is residue when Z prime goes to 0, so it's A equals 0, 1 over square root of Z prime square minus 0 square, so it would be 1 over Z prime. Basically, it's 1 over Z prime in this case. dz prime dz over Z prime minus Z to the square. So it's residue when Z prime goes to 0 of dz prime over Z prime dz over Z prime minus Z to the square. So this is just dz over Z square. Just evaluate at Z prime equals 0. And so the formula for Recursion 3, which is very useful, is this one. It is clearly symmetric in the 3 variables, by the way. And it makes computation very easy. It's just the evaluation of a line both. So now 5, I will introduce the FGs. So I will define the FGs of a spectral curve, and I will use the Bertrand equation for it. So let me make the definition. So somehow the FGs will be the same thing as the omega G0. Definition: FG of the spectral curve, which is the same thing as the omega G0 of the spectral curve, will be defined as 1 over 2 minus 2G sum over A residue Z goes to A of omega G1 of Z F01 of Z. This is valid only for G larger than 2. This is defined only for G larger than 2 because of this 2 minus 2G. You cannot take G equals 1, of course. And you could think of taking G equals 0, but if you take G equals 0, you would have omega 01 times, well, basically you would have F01 times the differential of F01, so it would be the differential of F01 square. On the residue of a differential is 0. So you would find 0 if you apply this formula for 01. So in fact, there is, well, let me just mention, there exists definition of F0 and F1, but beyond this lecture. So I will not do it in this lecture. It will go a little bit too far.
But F0 is 0 or 0?
No, it's not 0. F0 is not 0 and F1 is not 0. So, well, the fact is that very often, if you think about random matrices or formulations and so on, you would think, well, okay, F0 is the leading term in the large n expansion of a log of function, something like that. Since it's the leading term, it should be the easiest to compute. F1 is the next to leading term. It should be a little harder, but not so much. And F2 should be more complicated, F3 should be more complicated, and so on. Here in this formula, it's a little bit the opposite. All VFG with G larger than 2, the formula fits in one line. F0 and F1 are much bigger to write. In physics, it's also related to the notion of zero modes. F0 and F1 somehow involve zero modes, so there are more terms, whereas the FG with G larger than 2 don't, and they are somehow simpler to write.
So what is on the right of the formula, F0, 1? What is?
So remember, so it was defined before. Remember that F0, 1 is a function defined locally such that its differential is omega 01. It's any primitive of omega 01, and any will give the same result.
Sorry, but now, what do you mean by zero modes?
Okay,
Okay.
I don't want to. I'm just saying it is related. Just because it's related to the fact that basically everything which has 2 minus 2g minus n strictly negative is called stable. And 2 minus 2g minus n positive is called unstable. If you count surfaces that have this Euler characteristics, they have a finite number of automorphisms. If you count surfaces that have this Euler characteristics, they have infinitely many automorphisms. They have an infinite group of automorphisms. This is the notion of stability in the classification. So basically, all the stable, so basically, topological recursion is well adapted to the stable part, assuming that you already know the unstable part. But the unstable, there are only 4 unstable cases, which are 0, 0, 0, 1, 0, 2, and 1, 0. These are the 4 unstable cases. All the others are stable. So that means F0, omega 01, omega 02, and F1. They are the only unstable ones. So basically, we use the Dilaton equation to define FG. And then it will satisfy also the property of homogeneity. It's homogeneous of degree 2 minus 2g. If I take the Airy curve and find the FGs, in fact, you only find all the FGs are 0. So it's not a very interesting example. I will not consider the Airy curve. To illustrate my point, I will illustrate later the Palovey equation, where the FGs are the coefficients of the Palovey function. In the WKB expansion of the Palovey function, but let me now go to.
G and 0, that's for G larger than 2 or even 0 and 1?
Even 0 and 1. And it's due to the fact that the tau function for the Airy case is just, for this Airy curve, is just 1. And its log is 0 to a lot of. So graphical representation of TR. So in fact, each time I write this formula for TR, and I remember it by heart, and the way I do is because there is a nice mnemotechnical way to remember the formulas, all these formulas, by representing them as graphs. So remember the formula, which was that omega gn, omega gn plus 1 of z0, z1, zn was sum of A, residue at A, and we have this Ka of Z0Z, and here we have this big combination where you have omega G minus 1 and plus 2, and you have some sum of omega G1, 1 plus I1 of Z, I1, omega G2, 1 plus I2 of sigma of Z, I2. While here we put the Z sigma of Z on Z1, Zn. Okay, on no 0, 1. Okay. So let me represent it graphically. So let me symbolize omega gn plus 1 as a kind of blob with G holes and n plus 1 legs. Okay. I put one leg on the left, because it's convenient, we put Z0 on the left, but in fact it should be symmetric in all legs. And here in this term is an omega G minus 1 with n plus 2 legs, and n of the legs being Z1 up to Zn, and there are 2 more legs, Z and sigma of Z. And here you have G, and here G minus 1. You have also terms coming from the second line where typically you would have an omega with G1 and with a certain number of legs on the Z, and multiplied by an omega G2 with another number of legs. Typically this could be Z2, Z1, Zn, something like that. And you want to multiply this quantity here by the K and compute a residue. So a residue is an integration. So typically in Feynman graphs, making an integral is represented by a vertex. And this K is an object that has two variables. So let's represent it by an edge. And let me represent K by an edge from Z0 to Z. And let me put a vertex at the end, which I write this way. And it turns out that it's a property Ka of Z0Z is Ka of Z0 sigma of Z. Just look at the definition which was written before. It's obvious from the definition. I mean, the definition is clearly symmetric. So let me put sigma of Z here. And I just glue this here. And the residue means computing. The residue means compute. The vertex means take the residue at all branch points. Plus, and here you have this again this sum, and here again, yeah, kernel K. So basically, kernel K. Let me represent it as K like this. It is just a mnemotechnic representation. So basically, this picture means this function. And this is the formula, the topological recursion formula written graphically. But let me show you how to use it in practice. Let me.
Bertrand, in the second, in the three level, in the second part of the equation, on the output lines should be E1, I1, and I2 on the right.
I1.
The set I1 and the set I2.
Yes, so it's the set I1 and the set I2. But I just choose an example here. I1 was Z1 on Zn, and here I2 was Z2. Just an example, but you have to take the sum over all of them. So here it's G1 plus G2 equals G, and you take the sum over I1 and I2. I just want to say one more thing is that omega 02 will play a special role. So omega 02 in this picture should be the omega 02 of Z1, Z2, which is also equal to B of Z1, Z2. In this picture, it should be represented as this guy, so a sphere, means 0, with two legs. But let me represent it as just an edge, Z1, Z2. And since it is symmetric, I don't put arrow on it. The arrow will be only for K. Let's do a computation using this graphical representation. And you will see that, in fact, this is not just a graphical representation, it's actually quite powerful. And in fact, many of the proofs of the propositions I made before can be proved just graphically. And in fact, this graphical representation is very powerful. So example, omega 03 of Z1, Z2, Z3, according to this picture, is Z1, and here we should put, what should we put here on the right hand side? Well, since G equals 0, there is no G minus 1. In this case, G minus 1 does not exist. So we have this sum. And here in the right hand side, we should put something which has, so basically, it's, so G1 and G2 must be 0, and we are just summing over I1 and I2. And since we want to know 0, 1, and since G1 and G2 are 0, it means that I1 and I2 must not be empty. And the only possibility to split the set Z2, Z3 into two subsets that are not empty is to choose either I1 containing Z2 and I2 containing Z3, or the opposite, I1 containing Z3 and I2 containing Z2. So there are exactly two terms in the sum. And these two terms correspond to having some omega 02. And omega 02 is the line. So it will be either this one, Z3, plus this one, Z3, Z2. These are the only terms. So again, this picture has the following meaning. So the meaning of this picture is sum over A, residue Z raised to A. This is the meaning of the vertex. The kernel K, this edge is the kernel K, K Z1Z. This edge is the B of Z, Z2. On this edge, so here it was Z on sigma I of Z. On this edge is B of sigma I of Z, Z3. So this is just this picture means this formula. On the second one, the second picture means sum over A. Let's do with A, KA, so it is an A, of Z1Z, B of, now this is again Z on sigma of Z, ZZ3, B of sigma of ZZ2. So this formula, so this picture just means this formula. Well, you may remark that, as I said, Ka is symmetric by changing Z to sigma of Z. So in fact, these two terms are in fact equal, just by the symmetry. In fact, you could also say that this is 2 times this graph, where you put the 2 on the 3. In fact, the two graphs have the same value. Okay. Let me illustrate on another example. So I was just saying that each graph just means a formula on just a mnemonic way to remember the formula. Let me take also the example of omega 1, 1 of Z1. Then this is Z1, Z sigma of Z, times, and what do we have on the right hand side here? G equals 1, so G minus 1 exists. There is no other terms, so but you see this exists with an omega 02 here, so you could do an omega 02. And here, in fact, this sum is empty here because G1 plus G2 have to be equal to 1. So either G1 or G2 must be 0. And I1 and I2 was Z1 Zn, which is empty here. So both I1 and I2 have to be empty. But since either G1 or G2 is 0, it means there will be each of these terms will give a 0, 1, so they should not appear in the sum. So this is the only term. And so by definition, this graph means exactly sum over A residue Z goes to A, Ka, so I just reading it on the graph, K Z1Z times B Z sigma of Z. So this is just what I read from the graph. But now let's go a little bit further. Let's do now omega 1, 2 of Z1, Z2. Let's do omega 1, 2. So omega 1, 2, I just apply again the formula. So Z1, and here I have G minus 1 and plus 2 will be omega 1, omega 03. So I can do an omega 03. An omega 03 was something like that. Z2, and here Z, let me put Z on sigma of Z. So I include an omega 03. Plus, what do I have in the sum? You have either, well, you will see that we must have an omega 02 and an omega 11. Just apply the formula. So you could glue an omega 02 Z1, Z2 on an omega 11, so which was genus 1, like that. Plus, you also have the term where you put the omega 11 there, and the Z2 there. But now, let me replace this piece, this omega 03 here, and this omega 11 here, or here, by what we have already computed graphically before. So let me replace this part inside by these two graphs. or maybe in fact it would be easier for the overall. So here we put Z1, and here, so since omega 03 is symmetric in its three variables, if I want to apply the graphical representation that I have here, I have to choose one of the variables to be the entry point of the arrow. Let me choose Z. Let me put the arrow on the Z. So, so then this is this. And here now we have a Z2 and sigma of Z. And the sigma A and sigma of Z was there. Okay. Plus, and omega 03 was containing two graphs. So there is a second graph coming from omega 03, which is this one. And here you have two legs. But somehow this one is going to Z2. And it is that one that is going to sigma of Z.
You say that the two contribute the same?
Exactly. So I could, I will rewrite it with the symmetry factors after. But first I'm just plotting all the graphs plus this graph, the 2. On this one, I replace it by this graph. So there is an edge. On this graph, so indeed with the symmetry, all this is equal to 2 times this graph. So, plus 2 times this graph. Okay. You see each time, for example, omega 1, 2 is the sum of graphs that have one loop on two outer edges, two outer legs, of course. So it's a sum, omega 1, 2 will be the sum of graphs with one loop on two edges, two external edges.
Okay.
And you can repeat this. Sorry?
Can you just repeat why it's one?
I mean, graphically, I see, but
Well, yes, you see it graphically, but it will be a theorem.
okay.
But
So this means that because all the loops are generated by the first term in the expansion. So if I look at the sum, that generates the loop,
indeed, this is
and
what
the one is just three legs.
Yes, exactly. This is the one that generates loops.
And can you tune it like the intensity of the term? So just like expansion.
It is okay.
Yeah, but I mean, the other one is at 3 level, so it may be some subdefined of something. The rest,
Yes, there is a way to do that, but it's beyond what I want to say now. Well, let me just give you what is omega 2, 1, for example, to go a little bit further. So omega 2, 1 with these notations, and I'll let you do the exercise if you want. So it will be this one will become the factor 2 plus 2 times this one here plus sorry plus this one Okay, so this is just an example which you can easily compute. And again, it's a sum of many graphs. It's a sum of graphs where each graph has two loops on one outer edge. The outer edge is in fact an arrowed edge because all graphs must have an arrowed edge.
These loops are genus 0.
What do you mean genus 0? I'm computing omega 2, 1, which is not supposed to count.
Loops on the right.
Yes.
No genus.
What do you mean by no genus? I mean, these graphs are planar. But I'm just talking about this loop. You have two loops here. Yes, the graphs
There's
are
no more
planar.
genus in this function.
I mean, I think it's just saying
It's
that
something else.
if we go back, in the end, you get something with the G equal to 0. So for the next G equal to
The original genus is replaced by loops.
Yes. So now, yes. Basically, I've replaced the G here, the G that was there, has become the number of loops. And so, for example, just to tell you what is the value of this term here, the value of such thing. So here you have your Z1 here. It will be a K Z1. Let me give names to variables here Z and sigma of Z. Branch point A. This is branch point B. Let me put Z prime on sigma B of Z prime. And this is branch point C. And you will have here Z second on sigma C of Z second. Okay. So the value of this graph is, by definition, K of Z1Z times KB of Z Z prime. Then this one is the K of Z prime Z second. And here you have a B of sigma B of Z prime times Z second for the other variable. And here you have another B of sigma C of Z second and sigma A of Z. And we take the sum over A, B, and C in R, and residue at Z goes to A, residue at Z prime goes to B, and residue at Z second goes to C. So this is just what this graph means, this formula. Well, there is an important thing to remark. B and K have poles when the 2 points are equal. Or poles. Which means that the order in which you compute the residues does matter. So you need to compute the residues in a very specific order. But remember how I introduced those graphs? It was by recursively replacing from the left here. I was recursively replacing things by graphs I had already computed at the steps before. So in fact, in this picture, it means that the residue which must be computed first is somehow the last one when you follow the arrows. So this means that I should first compute this residue, then this one, then this one. So if you want, this is why I wrote them in this order. You first compute this residue first, then this one, then this one. And it will matter. So just to say it very simply, follow the arrows backwards. And in fact, also because I use the recursion formula to construct these graphs, it means that the arrows will never make loops. The arrows never make loops. The arrows always form a tree. So in all of these graphs, the arrows always form a tree. And this is where they start to differ from Feynman graphs. In Feynman graphs, if you have two types of edges, there is no reason why one type should only form two. It would be a non-local constraint, which Feynman graphs don't have. Here I have this non-local constraint that arrows must form a tree, which means also that there is less such graphs than Feynman graphs. So it's more economical than Feynman graphs. So on this will be kind of general. So the use for each graph represents the formula, and you have to compute the residues backwards following the order of arrows.
Yeah, so you mean that the arrows form a spanning tree of your graph?
Yes, they form a spanning tree.
To reach every vertex?
Yes, and it came from the recursive construction. I mean, at each step, you always have a k. There is always a k at each step, and you reach all the vertices, and every vertex is at the end of a k. There is no vertex that is not at the end of a k by construction.
Can you generate the trees with some, I don't know, I mean, if I just look at the arrows, then I have a certain point, and then the root should be some kind of random field somewhere that I just join, because it's very similar to random field.
You can, and this has been done. And in fact, you can even find a kind of generic function of such trees, which is in fact the airy function again.
Okay.
So if you want to count the number of such graphs, basically the generic function is given by the airy function. So you can evaluate how many such graphs you have.
You mean that there could be another way to generate or maybe it's equivalent to generate the graph by first doing the tree with the arrows, and then you match.
That's what I'm going to do right now.
Then you match the right.
But what I will do exactly now. So indeed, I wanted to write it as a theorem. So theorem that omega g n of z1 zn is the sum over graphs g belonging to a certain set of graphs that I will call big G of z1 zn, on which I will write in a minute what it is. But you have product at vertices of residue sum over A, residue at A. Okay. Product over arrowed edges of the K, and product over non-arrowed edges of the B. And what is this set G Z1, sorry, G index G of Z1 Zn? It's the set of graphs that have G loops on n external edges, on such that there are 2g minus 2 plus n arrowed edges forming a tree, a spanning tree. And rooted at Z1. There are n minus 1 external non-arrowed edges ending at Z2 Zn. Okay, and there are G internal non-arrowed edges. And there is a constraint. A non-arrowed edge can go only from a vertex to one of its descendants along the tree. Joining vertex to a descendant. Or a parent. I mean, basically, they cannot change branch. So, for example, a graph like that, I mean, this graph will be forbidden. This graph is forbidden. It never appears. You cannot have a non-arrowed edge going from one branch to another branch. It must go from, it must do, for example, that. This one is alone. The loops can never go from one branch to another branch. It's implied by the recursive construction. And that if we take all such graphs, you have, I mean, these are exactly the graphs that you contribute. And in fact, graphs have symmetry factors, and symmetry factors are always powers of 2. But you can just put all of them or. Okay. Yes, so one easy way to construct them is first, indeed, try to construct all the trees with 2g minus 2% edges. So you first construct all trees with 2g minus 2% edges, and then you fill with the rest. For example, we illustrate that for again immediately one. For example, G1, then 1. Sorry, GGN. Let me put GGN. One of Z1, by definition, first you find all the trees with 3, so 2g minus 2% is equal to 3. So find all trees. So first you make all possible trees with 3 edges. So one tree is this one, another tree, sorry, the trees must be trivalent. I should have said trivalent. Trivalent. So the tree, but the tree is not necessarily trivalent. It can be less than trivalent, because I will complete that by other things. What else we have? That's all. So now, what are the possibilities to complete with G with two loops? So one possibility here is to do this. This. So I can make one loop there, one loop there. I could also take one loop there, one loop there, and one loop there. And here, in fact, for this one, you have no choice. The only thing you can do is this. And indeed, these are the three graphs that I've written here. If you want to compute correctly the symmetry factor, take that each K has a left and right child that are different. So let's put, I don't know, a dot on the left child. And if you put the dot in different places, you find the correct symmetry factors. Okay. But you see, indeed, one way to get all the graphs is first to construct a tree and then. So it's a good time, I think, for a break.
Oui, c'est j'ai un crash. Tiens, c'est pas possible, toutes les fenêtres. Ça.
Bertrand, is there a graphical proof of a symmetry property?
Yes.
Are you going to do it?
No, but I was going to prove the dilaton property. When you contract with F01, you get minus switching by the same objective minus one. I was going to do this one graphically because it's very, very simple.
Okay, because the symmetry, does it boil down to local rule that belongs to reverse VHS?
Exactly. And this is how we did it, in fact. Exactly like that, graphically. And the proof is much easier when you use graphical representation. And indeed, in the end, you have to basically, in the end, it boils to prove that omega 03 is symmetry. But for omega 03, we have an explicit formula on this symmetry. So, I mean, yes, indeed, in the end, proving the symmetry locally boils to just proving it for around the vertex. If you want.
Bertrand, I think that these constraints are not are more general than topological recursion, because you have exactly that formula in for Polchinski equation, which has exactly the same structure. So I think that this kind of things comes from the fact that you have the exponential of something, and then you have the derivative of this exponential. But here I don't see your derivative.
In fact, it's related for example, it's related to, let's say, Vira-Zero constraints, things like that. So instead of Vira yes, okay, I agree. It appears in many places, but maybe it means that topological recursion appears in many places.
But the arrows for I will say that the arrows, you have conservation of momentum, and you have in endpoint functions, you have one point which is minus the sum of the other, and you have to follow this along a flow.
I'm aware that these graphs have appeared before in other contexts, typically in quantum field theory. And in fact, there is even a name for this set of graphs. It's just I don't remember it. Sorry. But it was named after someone who introduced it.
But what is proper to your problem is that you take the residues. I mean, in Feynman diagrams, you have to do loops, loop integrals, which is much more difficult.
Yeah, but I mean, in the because I mean, if you do Feynman graphs in the momentum representation or in the space. In the space, you compute integrals at vertices. And this is what they do. Integrals are at vertices. And in fact, residues are easier than integrals.
Yeah, but and then how to say, it's not a two-dimensional loop. It's say a four-dimensional loop.
However, I recall that this will compute also things in dimension 6, for example. In the end, we are computing things in, let's say, string theory in dimension 6 with this formula. And indeed, in the end, you just have to compute residues.
So you say that the 4 equal to a couple of
it means that the dimension of the space is somehow encoded in the spectral curve. In which spectral curve you choose. So the dimension is not something so, I don't know, I mean, this is one of the holography principles, but the dimension of a space is maybe not so crucial.
So we start with a break.
Okay, so welcome back. So first remark is that this graphical representation like that is very, I mean, if you would like to program the topological recursion on your computer, in fact, most of the part of programmation will just deal with combinatorial graphs. Then you just take the product of K, product of B, compute residues, like the easy part in the programmation. The main part is just to draw all the graphs. you can also recursive. But mostly, as Jeremy remarked, many of the proofs, many of the things we can do can be done graphically, and this graphical representation is very powerful. So now indeed, in all this graphical representation, it was always for n larger than 1. So we need always an external leg. So you see, by definition, the tree is rooted at Z1. So there is always a Z1. What can we have such a representation for the FGs, the omega G 0, n equals 0? Yes, somehow. Let me do it now. So find the FGs. So how can we represent graphically the FGs? And remember the formula for the FGs. So remainder. So then FGs. So remember that FG by definition was 1 over 2 minus 2G residue. So sum of A residue at A of omega G1 times F01. So I will take, well, let me write it the other one. F01 times omega G1. And remember, omega G1 was a blob with genus G and with one leg. And I will do it to F01, and let me represent F01 just as a big dot like that with one leg. And let me, for example, apply that to F2. Example F2. So this was 1 over minus 1 over 2 times. We had our graphs, so 2 times this graph plus 2 times this graph plus 1 time this graph. And we shall just glue we shall just glue the dot here, and the dot here. In fact, we cannot do much more than that. And let me prove the dilaton equation graphically. Which is, I think, 3 in chapter 3. Proof of dilaton equation. Graphical proof. So, remember that omega Gn is the sum of graphs like that. Let me illustrate with omega 1. Let's take the example of omega 1, 2. Okay, plus this one. Okay, that's omega 1, 2. Okay, we have a sum of graphs. And then we want to compute omega Bn times F01 on take residue in the last variable Zn, Z1, Z2. Residue at Zn is to A, sum of brackets. So in my example, I had, so this was omega 0, omega 1, 2 here, in my example. So let's take omega 1, 2 and glue the dots here to the leg which is not the root, Z2. So let's compute these graphs. let me represent your ounce. We put it here. Ounce. And we do the yellow dot. Okay, and just one way. So if you compute carefully, you will realize that each time you have this with two b's, 1k and 2b, and you glue you contract with the F01, 1 over b, this is 0. And each time you have 1k, and 1b, and you contract here with the F01, when you glue the F01 there, this is -1 of k. When you put, so it's like you have contracted the leg. And if you do that, you see in this example that when you contract the leg here, you will get -1 of. So you get -1 of. So you get 2 times -1 of, and you just contract that leg, so you get this one. And here you get 0. No, sorry, this is the opposite. Here you get 0, and here you get this one. 2 times -1 of, so you get a -1. There's something wrong with the factors, but okay, just to give you an idea of. But basically, this can be, so the dilaton equation can be proved graphically. So basically, contracting F01 with on a vertex like that will just, basically, it's just like erasing it. And here it gives 0, which means that in the end, you're left with a sum of graphs with one edge contracted, and you realize that you get the same graph as for the omega gn plus 1, but you get it many times as you could have inserted a leg, which is proportional to the number, which must be equal to the number of cases where you could insert a leg, and the number of cases where you could insert a leg is precisely 2g minus 2%. So, just to say that the dilaton equation is extremely easy to prove graphically. And indeed, the symmetry can be proved graphically, but I'm not going to do it. So now I want to go to another thing with the graph. So for those who are right left, I just say that I represent F01 as the yellow dot. And you just do it by taking residual operation. This is the formula for F2. Okay, so now there is another graphical representation that is very useful. So it's the 3D graphs. So now let me review all these graphical representation again, but instead of writing graphs with edges and vertices, let me represent now things with omega gn, or z1, zn. Let me somehow thicken the edges, and let me represent it as a guy like that. Minus g, z1, z2, up to zn. Okay. It's another representation, graphical representation, meaning the same thing as before. Again, it's just a symbol. It has no meaning by itself. It's just a symbol. And the topological recursion says that this is sum over A residue at A, on which will be the operation of gluing, will be the correspond to gluing. And I will, so in the left hand side, I have this omega g minus 1 n plus 2. So this one has d minus 1, d. And I will glue it to get this Z1 here. And the way you want to do it is to, so you could think that you want to make a pair of points like that. But in fact, the K has only two variables. So somehow these two variables have to be, in some sense, the same, or one is Z and the other one is sigma I of Z. In fact, it has only two independent moduli. So in fact, the way I choose to represent it is by doing a kind of cylinder, but with a pinched boundary. And this is going to be K of Z, sigma I of Z. K A of Z1 Z. On the gluing, it's just that we glue this guy to this guy, and this guy to this guy. Plus, and we have the sum of G1 plus G2, and I1 and I2, and no disk, no 0, 1. Same thing. And here you can with this picture, for example, the formula above with, let's say, omega 2, 1, or omega 1, 2, the picture of omega 1, 2 of Z1, Z2, which I had before with graphs. So if you want, these are the same graphs as, so A of Z1, Z is now represented in this way. And B of Z1, Z2 is just a cylinder. So, for example, well, the graphs I'm going to get are just somehow the second version of the graphs I was writing before. But it's very convenient and very inspiring to write it this way. So, for example, this one was this one. With 2 times this graph plus 2 times this graph. One. Which is the same formula as I was writing before. So again, what does mean such a picture? This picture means that you will multiply a K here, a K there, a B on a B, and the gluings of each time you have a gluing, you take a residue. And again, you go backward following the K to complete the residues. So it's just the same picture as before. And now the operation of gluing an F01 is just like gluing a disk to close the boundary. So just gluing a disk and you close the boundary. And this formula, for example, means that when you do that, and you glue a disk here, you get basically this one again with a vector -1/2, I think. And it's very inspiring. And I recall the formula of K. Remember that K was 1/2 of the integral of B so Ka of Z1Z was the integral from Z prime to sigma of Z, Z B of Z1 Z prime, divided by omega 01 of Z minus omega 01 of sigma A of Z. So if you think about it, it means that, well, take the example where omega 01 has is invariant under the involution, then the denominator will just be 2 times omega 01. Just take this as an example, which is the case for all degree 2 curves. This means that K times omega 01 is the primitive of B. So if you want, this means that if you take omega 01, so if you take K and glue indeed a disk, you get a B. Well, you don't get exactly B, you get B with you get the integral of B, and to be correct in the representation, each boundary should have a marked point, and here there is a natural marked point, which is the pinching point. But so everything should have marked points, and taking the integral means forgetting the marked points. That's what it means. Okay. So the pictorial representation of the definition of K is somehow this formula, meaning that when you glue a disk to K, you should recover cylinder.
Bertrand, the pinch is just graphical. I mean,
Yes.
you could have chosen a different color for that, to draw the pans for K.
Yes. Yes.
For instance, okay, it's nothing physical.
No.
Okay.
Unfortunately, in fact, for a long time I was thinking that maybe there is a way to prove, for example, when you in the string theory context or in the combinatorics of maps, triangulations, and so on, I was hoping to somehow find explicitly these curves in a canonical way to cut the surfaces or the triangulations along such curves that had a pinching, so that we would get exactly the topological recursion as a bijective thing in combinatorics of maps or in string theory or in hyperbolic surfaces. So in hyperbolic surfaces with Mirzani, it's very canonical way to cut pair of points at some places, and it turns out that no. And now we understand why. Related to the Max chain, I don't want to go into the details. So we understand why, and basically, no, there is no canonical ways of cutting that would exactly do what the topological recursion is doing. So now let me move to the next part, which is to study the notion of deformations. So the question is, what happens when we have a family of spectral curves and we take derivatives? Do the omega GNs will satisfy nice equations with respect to varying the parameters? Will they satisfy nice differential equations? And it turns out that yes, they satisfy very, very nice structures. They satisfy what's called, it has several names depending on the context, but you can call that special geometry. In other contexts, you would call that Taylor-Witten. In other contexts, you would call that Niwa-Jimbo. On many other things. But so basically, it's in the context in TR, this is all the same equation in the end. They are all the same thing. And basically, these equations appear in string theory, in gauge theories, in integral systems, on many things, but they are always there when you have TR. Let me consider an example. So one example. So let's take the family of spectral curves that we call S2. It would be the family x equals z squared, y equals z minus 1/4, sum from k. I will say a moment what k I will take. K plus 2, 1, zk minus 2. And I will start with k larger than 3. And let me stop somewhere at some degree d, whatever. And d is d of z1, z2 is dz1, dz2 over z1 minus z2 to the square. So this is the family of spectral curves. And now let's start to compute. So now I would like to compute for every family of times. I would like to compute fg of these times on z1, zn. And what I want to compute is d over dtk of omega gn of t z1, z2. This is what we would like to compute. To really satisfy a nice equation. The answer will be yes, and in fact the proof again will be graphical. The easiest proof is graphical. Okay, so let me start by first computing the derivative of omega 01. So omega 01 is y dx. So in this context, it is dx is 2z dz, and I multiply it by z minus 1/2 sum over k, dk, zk minus 2. Well, here I restrict to k strictly larger than 3. All what I'm going to tell about works also for k smaller than 3, but there are some more technical details, so k larger than 3 is easier. So it is 2z squared dz minus 1 minus sum over k of 2k z k minus 1 dz. By the way, it's easy to compute f01 in this case. F01 is 2/3 of z cube minus sum over k, 2k over k, z k. And this is why I took this shift of k minus 2. It's because I want to have zk with tk in the f01. But what I want to compute now is d over dtk of omega 01. So, in fact, to be precise, I should say take the derivative of omega 01 of z at fixed x of z. But in my example, x of z does not depend on the times. So it's just computing at fixed z. But in more general context, you should work with fixed x and not fixed z. Somehow z is a dummy variable to parameterize your curve. What really matters is the value of x. So let's compute. Well, this is very simple. This is minus z k minus 1 z. Okay. So far so good, but I would like to write it in another way. Let me remark that this is indeed the derivative of z to the k over k. The differential of z to the k over k. And a differential can be computed by taking a residue of a double pole. A residue of something which has a double pole will compute the derivative. I mean, it's a general property that residue of f of z prime dz prime over z minus z prime to the square when z prime goes to z is equal to f prime of z. Of course. And if you multiply by dz, you will get that, which is the same thing as df of z. Okay. So this may look a strange idea to do that, but let's do it. So let me write it as minus residue at z prime goes to z of z prime to k over k times this formula which I just wrote was exactly the b of z prime. So which is dz prime over z minus z prime to the square. Now observe one thing. This has a pole at z equals z prime, which is what I use, but this one has a pole at infinity. And the sum of all residues must always be 0 for every meromorphic form. So which means that this is plus the time residue at z prime goes to infinity of z prime over k p of z, and let me write it now as omega 02 of z prime. Okay. So let me write it in this way. d over dk of omega 02 of omega 01 of z. Let me write it z1 equals residue at z goes to infinity of z to the k over k omega 02 of z1 z. Just a remark. Now let me do the same computation with, let me now compute the derivative of d over dtk of omega 02 of z1 and z2. Well, it's 0 because omega 02 will not involve pk. Okay, it's obvious. But let me now compare to another computation. Let me compare with residue at z goes to infinity of z to the k over k omega 03 of z1, z2, and z. Okay. I encourage you to compute this omega 03. I gave a formula computing omega 03, and remember it was -1 over x second of 0, y prime of 0, times this BA of Z1, Z2, the product of BAs, which were product from I equals 1, so which was dz1 over z1 square, dz2 over z2 square, and dz3 over dz over z square, times on x second, the second derivative is equal to 2, the first derivative of y is equal to 1, so it's -1 whole. So this is -1 whole. And here, remember that I'm taking k larger than 3. So zk divided by z square has no pole. So this residue is 0. Well, so basically the two are equal. Okay, so you see, when I act with d over dk on omega 01, I get a certain integral on omega, a certain, yes, residue is like an integral. I take, or if you want, I have a linear operator acting on omega 02. When I compute the derivative of omega 02, it's equal to the same linear operator acting on omega 03. Okay, so here it may look like a coincidence, but in fact, this is general. And this is really what is called special geometry. So I should maybe not erase that out of the way. And so this is a theorem. If okay, so let me state the theorem in this case. For every Gn, such that 2G minus 2 plus n positive. No, in fact, this is sorry. It's true for every Gn. Sorry. T over dtk of omega Gn z1 zn equals residue when zn plus 1 equals to infinity of zn plus 1 to the k over k times omega g n plus 1 of z1 zn plus 1. So this is true for this family of spectral curve, but in fact this is true also in general.
But then sorry, what is K? I mean, if I just take a deformation, whatever.
Yeah. So in fact, so I will explain that in a second. So here the K was the index of a TK.
Yeah.
And the 1 over K really came from the fact that the parameters was really something like T over K.
Mm-hmm.
It's more, it's deeper than that. Okay. But yes, there is a theory of to a tangent vector. How can you associate a linear operator acting on form? There is a general theory of that. So typically, a linear operator acting on a form can be represented as a kind of integral on something. Well, something with a weight here with Jacobian, but it's a kind of integral. I used to call that generalized cycles. Like an integral, usually you take integrals on cycles, but here you have to introduce some slightly more general function, which I call generalized cycles. And there is a kind of correspondence between tangent derivatives, which means tangent vectors, and cycles. There is a correspondence between derivatives and cycles, which is well known in many contexts like machine systems. Like that. So, I will show you how powerful is this equation in a moment. But I just want to mention about the proof. And first, also generalize this theorem. So first here, I stated the theorem only for that curve specifically, or that family of curve. Let me write it in a more context. Yes, and also the link to special geometry is that special geometry is precisely the statement that the derivative is an integral of something. And indeed, if your curve will be, for example, a torus, and you want to take a derivative with respect to the value of a cycle integral, what you find with this way is that the derivative with respect to the parameter corresponding to a cycle integral is replaced by the integral over the b cycle. And that's Seiberg-Witten equation. For those questions you know. Okay. Let me state it in more general theorem deformations. If there exists well, let's say, let me call it a linear operator acting on forms, on one forms, neuromorphic one forms. Or this is also what I will call the generalized cycles. Well, let me say, let's start with, we have a one parameter family. ST such that d over dt of omega 01, and let me call this one, let me call it gamma t. D over dt of omega 01 is gamma t acting on omega 02, and d over dt acting on omega 02 is the integral is the gamma t acting on omega 03. Then, for every d on n, d over dt of omega gn is gamma t acting on omega gn plus 1. So if it's true for 01 and 02, then it's true for all of them. The proof is quite simple graphically. Let me start by the second the second equation. So now I'm just saying that d over dt z1 z2 is omega 03, and omega 03 was this graph. And here I act with gamma t on one of the two left, plus so omega 03 was containing two graphs. Okay. So which is 2 times, which is by the way 2 times this one. Okay. So this first equation means that graphically. So the first equation, so basically the second equation here means that when you derivate this propagator, it's the same thing as replacing it by, let me write it in this way. Well, let me put a factor. So this equation is just saying that d over dt will insert a new edge in the middle. So yes, if you want to compute d over dt of the arrowed propagator, z1z, remember that this k was containing b in the numerator and omega 01 in the denominator. You know the derivative of omega of b here. You know the derivative of omega 01. When you combine the two, these two derivatives, it gives exactly that. Or in fact, sorry, instead of it here, let me put it this way. So basically, these two equations imply that graphically the edges satisfy this. And then if you put that in the recursive construction of a graph, it's obvious that it will imply that. This is really the part that was about the equation. This graphical method was really the one you could check off. Okay, so the proof is mostly graphical. So now let me apply it to our specific family. So to this family, what do we get? So we have to erase something. So I'm going to erase that. So let's look at an application. So application, which probably number 3. To the intersection numbers. So I'm continuing this spectral curve. And remember that when the t are 0, what we get, what we obtained the other day, I showed you, was that omega gn of 0, z1, zn. I told you this is a polynomial, and I put a -1 to the n, I put a 2 to the 2 minus 3 to minus n. And this was a polynomial in the zi's, which falls only at 0. Okay? So it was a rational fraction, which falls only, sorry, it was a polynomial in one of the zi squares. And zi, so it's sum over d1 plus dn equals 3g minus 3 plus n. Let me call the coefficient cgn of d1 dn times product over I equals 1 to n. And you have something like zi equals 2di plus 2 gzi, and it's convenient to put a 2di plus 1 double factorial as a combinatorial factor. And remember that these guys who are called so in the Witten's notation they are called tau d1, tau dn d, which is just the Witten's notation to write this coefficient. And these are the intersections. So now I would like to do the same thing when we have t non-zero. So when t is non-zero, in fact, for the same reasons, we know that omega gn of t z1 zn must be a polynomial in one over the zi squares. It will not necessarily be homogeneous of degree 3g minus 3 plus n, so g1 dn. All what we know is that their sum will be less or equal to 3g minus 3 plus n, which is by recursion, but they are not necessarily equal. And let me write cgn of t d1 dn. Product from I equals 1 to n of 2di plus 1 double factorial zi over zi to 2di plus 2. So again, from the general principles, general properties of topological recursion, we know that this guy is going to be a polynomial in the 1 over zi squares because it can have poles only at the ramification points. And I'm just writing the most general form, and I call the coefficients with this name. It's just I'm just writing the general form of a polynomial of 1 over zi squared. For the moment, I have said nothing. But now I will use the deformation equation to write a differential equation satisfied by the coefficient, and we can even solve this differential equation. Now apply the differential equation, which is written here. So let's take a d over dtk of the left-hand side and compare it to the residue of in the right-hand side, and see what equation will follow from the CGNs.
Sorry, why do you know that the total degree is bounded in this case?
Well, okay, let's say you don't know it. Let's imagine you don't know it. Well, just by the recursive procedure, you can see that there is a maximum degree.
Okay.
Well, I agree, it's not obvious. So let's just write it this way.
No, because it was not in the previous theorem you cited.
Indeed, it was not. So let me, okay, it will be the case, but let's make as if we don't know it. All right, let's not know it yet. So let me now apply this theorem. Of course, it's only for the stable one. So let's apply it to this theorem. Let's apply the theorem to that. So the left-hand side is -1 to the n, 2 over 2 minus 2g minus n, sum over d1 dn, d over dtk gn of 2 d1 dn, product of 2di plus 1 over factorial zi to 2di plus 2 zi, I equals 1 to n, should be equal to -1 to the n plus 1, 2 to the 2 minus 2g minus n minus 1, sum over d1 dn and an extra d, 2gn plus 1 of t d1 dn and d times product, and let me separate the product with the first n on the last one. Product from I equals 1 to n of 2di plus 1 over factorial zi or zi with 2di plus 2. And let me multiply again by 2d plus 1 double factorial z with 2d plus 2 dz, and I multiply by z with k over k. And I take the residue, and z goes to infinity. Okay. This is easy to see, but guys, okay, it implies that Cg, so d over dtk to Cgn is minus 1/4 sum over d Cgn plus 1, sorry, Cgn d1 dn, Cgn plus 1 d1 dn d times this residue 2d plus 1 double factorial over k times this residue is just delta k 2d plus 1. Sorry, minus. In fact, let me put the minus. So it's equal to minus times. This is the computation of the residue, but the residue is non-zero only if you have a z to the power of -1, so k must be equal to 2d plus 1. And when you take a residue at infinity, there is a minus sign.
Same concept because you have the -1 to n plus 1.
Yes. Yes. So, and in the end, this will be so you see that first this is 0 if k is odd, is even, 0 if k is even, and if k is equal to 2, so and when you take t to the 2d plus 1, Cgn, d1 dn, this is minus and minus cancel, so it's 1/4 of 2d plus 1 double factorial divided by 2d plus 1, it's 2d plus 1, 2d minus 1 double factorial, Cgn plus 1 of c on d1, dn, and d. Okay, so this is the equation that we get. Okay. And okay, let me erase that. We're almost done because this is a first order linear differential equation with constant coefficients. So the solution is typically an exponential. Well, let me solve it by well, in fact, the nice way is to write the Taylor series, and this is why the Witten's notation is particularly helpful here. And let me write the. So remember that when t equals 0, we had that CGN d1 dn was equal to tau d1 tau dn. Okay. If you want to start, so then let us start by doing the Taylor expansion. Plus sum over k, tk, d over dtk evaluated at tk equals 0 of CGN. Okay. And so which will be 1 of 2k minus 1, sorry, let's put so somehow the 2d plus 1, 2d minus 1 double factorial, tau d1, tau dn times tau d. Plus, if you want to continue the Taylor expansion, 1/2 of sum over d and d prime, d plus 1, d prime plus 1, 1 over 2 to the square, 2d minus 1 double factorial, 2d prime minus 1 double factorial, tau d1, tau dn, tau d, tau d prime, and so on. And in the end, when we sum all the full Taylor series, one way of writing it is the following: tau d1, tau dn, and exponential of sum of 1/2 sum over d, 2d minus 1 double factorial, tau 3d plus 1, tau d. This is CGN evaluated at any t. The definition of this exponential of taus is you take the Taylor series. It is now obvious to see that this satisfies the differential equation. This is the solution to the differential equation. This is kind of obvious. Now, here you have an exponential involving many tau d's, but the definition, in Witten's notation definition, an intersection number like that is non-zero only if the sum of degrees is 3g minus 3 plus n, which means that in fact, when you do the Taylor expansion here, there is only finitely many terms. In fact, an exponential is a polynomial of intersection numbers. So this is the general solution. I should stop, but I'm very close to the recursion now. So maybe we continue next time. Well, what time should I stop?
As you want. If you need, I don't know if it is a good point to stop or not. Maybe yes.
Well, I think that it still takes a little time to do the next part. So, okay. So I think I should stop here.
So, okay, we can. Thanks. Are there questions? Also in the virtual room, in principle, you can take the microphone and ask questions. In the real room, we have a question.
So, if k is even, we have all of these things. And what happens with times that are odd?
Well, no, sorry, it's the contrary. The even times do not somehow the derivative is 0 for even times. So in fact, the CG ends do not depend on the even times. They depend only on the odd times, and that's why you have yes, only only the odd times appear in the formula. The even times do not appear. Everything is independent of the even times. And in fact, it is kind of obvious because the denominator in the K was omega 01 of z minus omega 01 of sigma I of z. So by doing this difference with involution, you kill the contribution of all the even times. So in fact, the even times don't appear in the K, so they don't appear in the omega GMs. Well, the idea will be now that, well, I'm just going to give you a small hint. When you take the spectral curve x equals z squared and y equals minus 1 over 4 pi sine 2 pi z, you can write this as an expansion. Well, okay, no, sorry, let me take this one, 1 over 4 pi. You can write this as an expansion sum over, let's say, tk, zk minus 2. And indeed, the first term is the k, is the z, plus sum over k larger than, so we take 2k plus 1, plus 2k minus 1. And this is k equals 2. When you do that, you see that this sine function is associated to a certain value of the times. You put this in the formula, and the idea is that this exponential, when you take exactly the times that correspond to the sine function, this exponential with the 2k minus 1 double factorial will be exactly what's called the Weil-Petersson class in algebraic geometry. And then it means that the omega GNs which you compute in this formula are exactly the Weil-Petersson volumes. Or if you want stated in another way, there is a theorem in algebraic geometry that writes the Weil-Petersson class as a combination of intersection numbers, and it is the one that corresponds to some very precise value of the coefficients here that are precisely what that correspond to this spectral curve. This is one way of proving near time resolution.
But you mean that the t's are fixed with the values from sin z?
Yeah.
Okay.
Mechanism. Basic formula, so Weil-Petersson class equals exponential sum of minus 1 to k over k factorial okay. Okay. The weighted constraint class is equal to that. And when you take this spectral curve, the times that correspond to the expansion of the sine function are exactly those that give this exponential. Well, you can call it Volter's, it's due to Volter's formula. And there are many similar formulas. For example, the Hodge class is also a certain combination of intersection numbers. It's called Mumford formula. And when you do that, you can try to see what is the spectral curve that will give the Hodge class, and you will find the Lambert function. And if you want to take what's called the topological vertex formula in string theory, you have a product of three Hodge classes. Can you find the spectral curve such that when you do this manipulation, so what is the spectral curve such that this series here will be a product of three Hodge classes, and it is when you take precisely the spectral curve to be the mirror curve of the Calabi-Yau threefold C3. For those who know string theory, this is one way of proving that topological recursion computes invariance in algebraic geometry. It's basically to use, on all of them, basically use this formula. And you see that if you know what the shape you want here, to recover the y, you have just some simple things to do, like divide by this 2d minus 1 double factorial, and re-expand that as the coefficient of the Taylor series, so re-multiply by some factorial, and this can be thought of as a Laplace transform. You can do that. This operation of multiplying by some factorials on the coefficients can be done by Laplace transform, and in fact, you can, the relationship between the class that appears here and the y is a Laplace transform, and so in practice it's extremely simple to do. Well, I think we have stopped.
Okay, so are there other questions? So let us stop here. We will see next Friday.